big theorem we are going to prove is the existence of the infinite volume free energy. Okay, so before going into this proof, let me recapitulate what we did so far. So what's the Ising model? So it's a probability measure on a set of spin configurations. So okay, so I call this state space omega lambda, where lambda is a subset of ZD, which is finite. And given beta positive, okay, given basically 2 parameters or 3 parameters, some positive beta, which we call inverse temperature, some H, which is real, which is the external magnetic field, and some eta, which is either an element of minus 1, 1 to the ZD. Okay, so the state of spin configuration on ZD. Okay, so it can be either this or it can be uniformly 0. The case where eta is uniformly 0 is called the case of free boundary condition. So this eta is a boundary condition. So given all of this, we define the Ising measure in the set lambda with inverse temperature beta, external magnetic field H, and boundary condition eta as the probability measure on omega lambda, which to each configuration gives a weight proportional to exponential of H sigma, where H sigma is equal, okay, so you have 3 terms. So you have the spin-spin interaction term, so x lambda, y lambda, x neighboring y. And, okay, I might have been, okay, let me write it like this. Just make sure. I mean, we are counting over unordered pairs. Okay, so x, y, and yx is the same thing. Okay, so I might have made a. So what you can do is instead sum over x in lambda, y in lambda, but in that case you have to take half because you're counting twice. Okay, so this is a spin-spin interaction. This is the effect of the magnetic field. And you have this last term, which is the boundary interaction. Okay, and this Z here, okay, okay, I'm forgetting about all the indices and exponents, but it's just what you need so that all these weights here, if you sum over sigma, you get 1 because it's a probability measure. So we had defined the free energy, or more precisely, the finite volume free energy, as follows. So we say that F lambda eta beta h is equal to 1 over lambda log z lambda beta h eta. Okay, what we had seen about the free energy is that it is convex, and if you take its derivative with respect to h, what you get is the average of the normalized magnetization. So let me recall what that is. So m lambda, it's just, well, the empirical average of the spin in the box lambda. So when I mean empirical average, I just sum all the values and I renormalize by lambda. Okay, so that's kind of the first motivation to study the free energy. In fact, we'll see that there are much more, but what we are interested in is really, well, some phase transition that concerns the magnetization, okay? So the Curie phase transition. And therefore, there should be some information contained in the free energy. So we are interested in the large volume limit of the system. So what we should try to do is take larger and larger box and see if this thing converges to something. So what I told you last time is that it does. And basically, we had started to see some ingredients to prove the theorem. So let me write the theorem here. Yes. Thank you. Yes, and I forgot to stop for questions. So please, if there are more questions, and please ask questions even if I don't ask for questions. Okay, well, it didn't work that time, but okay. So okay, what's the theorem? Yeah, I forgot about the last notion. So. When we take a sequence of box, growing sequence of box, and we want to take the limit, we want to make sure that, the limiting behavior is not dominated by the boundary. So for this reason, we enforce that lambda n grows in a certain manner, and this certain manner is just saying that the relative size of its boundary goes to 0 when n goes to infinity. And this is what is called converging in the von Hof sense. So Okay, and I'm using this absolute value bar for cardinality. Sometimes I'm using this hashtag thing. But, okay, so and the theorem is that if lambda n increases to ZD in the Van Hoff sense, then the limit when n goes to infinity of f lambda n eta beta h is equal, well, this limit exists and does not depend on eta. Okay, just maybe a small comment before we start the proof. So actually, yes. So well, first something on notation. So I don't know if I will use this notation very much, but it exists. So sometimes instead of saying this, what we can do is write the following. So to say that the convergence, okay, if I write the limit when lambda goes to ZD with a double arrow, like this, of f lambda beta okay, what I mean is exactly the above. I mean that this convergence occurs along any sequence that converges to ZD in the Van Hoff sense. Okay? So that's the first thing. Second thing is that actually you will see in the proof that we will not use this, we will not use this, we will only use this. Okay? And the fact that, sorry. Limit when n goes to infinity. Okay, so just to say that here really, yeah, this is the only important part. The fact that the volume goes to infinity and that the boundary grows in a slower rate than the volume. Okay, and if you remember what we did last time, was to, we had some consideration about superadditivity, which I will recall now. But the first thing we showed is that, well, the limit, if it exists, it does not depend on the boundary. So what we will do now is really restrict ourselves to the case eta equal to 0. Okay, so last time was yeah, it wasn't okay. So last time we saw that f eta lambda beta h minus f eta lambda beta prime. Okay. So this thing was smaller than 1 over lambda times 2 beta delta lambda. Okay, where delta lambda is the set of edges going out of lambda. Okay, so therefore we can consider eta g without loss of generality. Okay, here delta lambda is just the set of xy in E x in lambda, y in lambda c. Okay, and this thing is, of course, comparable to this. So this thing goes to 0 when lambda increases to ZD in the Van Hoff sense. Okay, so this reduces the proof of the theorem to the case where eta is identically equal to 0. So this was the first thing. So A, this was about boundary condition. B, what we saw something about superadditivity, I guess. Okay, so let me rewrite it. So let me define f bar lambda. Okay, beta and h are fixed, so I'm not writing the dependence in them here. So let me write this being equal, define this as being equal to log of z lambda beta h 0 plus beta times the number of edges in lambda. Okay, E lambda is just set of x, y in E such that x, y is in lambda. Okay, so basically, I mean, what we did last time was to add this term to the Hamiltonian, but if you add it to every configuration, I mean, it's just the same thing as adding this term to the log of the partition function. Okay, so defining this, what we saw last time is that if lambda 1 and lambda 2 are disjoint, then f lambda 1 union lambda 2 it is larger than f of lambda 1 plus f of lambda 2. Okay, and I mean, basically, the reason why this is true, okay, was basically just the fact that h lambda 1 sigma 1 plus beta e lambda 1 h bar is lambda is equal to h lambda plus beta lambda. What we had was that h lambda 1 sigma 1 plus h lambda 2 sigma 2 was smaller than h lambda 1 union lambda 2. And okay, 1, I should put it here because I'm using indices for the vertices of my graph. Okay, so for sigma 1 belongs to omega lambda 1, and sigma 2 belongs to omega lambda 2. Okay, so basically the idea is was that by adding this constant term to the Hamiltonian, we would make it subadditive in this sense, and this translates into superadditive in this term, in this sense, and this would translate into superadditivity for the log partition function. Okay, so supermultiplicativity for the partition function. Okay, and So this is superadditive. And of course, you can play the same game but deleting beta E lambda. And in that case, you get a subadditive function. And it's exactly for the same reason, okay? Basically, if you delete, okay, if you subtract beta per edge, basically, then you will get that the edge contribution will be beta times sigma x, sigma y minus 1, so it will always be negative. And this means that the edges between boxes, basically, they will have a negative contribution, so this will yield this inequality. Okay, so for the same reason, what we have here is that f hat of lambda 1 union lambda 2 is smaller than f hat of lambda 1 plus f hat of lambda 2. Okay, so now I don't know if you remember when we established the existence of the connective constant for the simple random walk. We used subadditivity, I guess, yes, or submultiplicativity. And well, the idea was to use well, Euclidean division. I mean, okay, what we proved the statement was that okay, if you had if an was a if Cn was a submultiplicative sequence, then Cn to the 1 over n was convergent. And what we did to prove that was to consider Euclidean division of n by a large number. So we are going to use a similar idea here. Basically, when we are going to have a large box, we are going to basically divide it into cubes, okay? And like an Euclidean division, like we will not be able to fit cubes everywhere. There will be some rest. But the fact that lambda n goes to ZD in the Van Hove sense kind of guarantees that the rest is negligible with respect to the full volume of the box. Okay, before I continue, any questions? It can be question about the writing. No? I don't write very well, so you're okay. But and sometimes I'm lazy. I'm writing over the existing equation, not to write things again. But, okay, but is everything okay? Okay. Okay, so the first thing we need to. Okay, so maybe now you know what converging in the Van Hove sense means. So I can erase this. Okay, so maybe the first thing we will do will be the following: show that if lambda goes to ZD, then E lambda over lambda. Okay. Goes to 0. Goes to, sorry, to D. Okay, I mean, I want to make sure that if I establish convergence of f bar of lambda over the volume of lambda, then I'm done. Okay, and the idea is that this second term here, it will converge. So if this over lambda converge and this over lambda converge, well, then you have the convergence of this. Okay, so what's 2D times the number of edges in the box? Well, okay, let me write it without n. Well, it's just I'm summing over all x's in lambda, then I'm summing over all y neighboring x, y in ZD, y neighboring x of 1, okay. Okay, so basically it's the same as, no, sorry. I'm sorry. I'm starting with this. Okay, so 2D times the number of vertices, it's the same as summing over all the, so summing 2D over all the vertices, and 2D, I just can write it as this. Okay, and now this second sum, I can divide it into two parts. Depending on whether y is in lambda. Okay, so this first term here is just twice the number of edges, okay? Because I'm counting every edge twice. Because I'm counting pairs, I'm counting couples instead of counting pairs. And this second thing is exactly delta lambda. Okay, so what we have is that 2D lambda n over, okay, sorry. What we have is that 2D, okay, I'm going just to divide everything by 2 times the volume. So I have D, which is equal to E lambda over lambda plus delta lambda over 2 lambda. Okay, and we saw that this thing is smaller than 2D times the size of the boundary of lambda. Okay, so by definition, if lambda n converges to ZD in the Van Hoff sense, this goes to 0, so this means that this has to go to D. And this ends the proof of the lemma. Okay, so now we can try to prove this, and what we are going to do is, okay, first, we are going to show convergence for specific sequence of lambda n, which does not converge to ZD in the Van Hove sense, but which grows in a way that the boundary becomes negligible to the volume, which is an important bit. Okay, so what we are going to consider is, well, let's imagine that we are in 2 dimensions, so I will call them square, okay? It will be d-dimensional squares. Basically, I want that at each step, my new square is a multiple of the square in the previous step. So I will just take the size of my squares to grow exponentially. Okay, and to make this thing as simple as possible, I take 2 to the n as the diameter of my square. So I will just choose dn to be equal to 1, 2 to the n to the d. Okay, whereas these double brackets here is just mean that AB is just AB intersected comes with Z. Okay, so just integer intervals. Okay, so just think D equal 2, because this is how I will do my drawings. There is no difference when D is equal to, when the dimension is larger. Okay, so what I have is that I can write dn plus 1 as a disjoint union of 2 to the power d copies, if you want, of dn. Okay, I mean, I can just split all my coordinates at half, okay, and consider all the subcubes I'm obtaining. Okay, so this is just the union. So I'm using this square for disjoint union. Okay, so and what I say is that dn plus 1, I can write it as a disjoint union of dni, where dni, it's just dn plus 2 to the n times I. Okay, where I runs over all, okay, so I is a d-dimensional vector whose coordinates are either 0 or 1. So you have 2d possibilities, 2 to the power d possibilities. Okay, 2 possibilities for each coordinate. So I mean, what I'm really saying is that right. Okay, all these squares are of equal size. And what I'm saying is that here, strictly speaking, I should put 2 pairs of brackets, you know, because I is a vector, so it has brackets, and then I have brackets there. So if you forgive me, I will just put 1. Okay, and you see, I mean, this is 0. This is 2 to the n plus 1. Okay, so dn plus 1 is just obtained by taking the union of 2 to the power d copies of dn. And now comes something which is quite important for the proof and which we didn't talk about so far. It is that, well, this thing is not really important here as far as f is concerned. So what you have is that f of lambda plus x is equal to f of lambda. Okay, and by the way, yeah, it's lambda plus x, it's, well. Okay, this is just the most natural. The definition of this is just a natural one, okay? It's the box lambda translated by x. Okay, so why is that true? Well, it's just because when you define z lambda, it's actually something that just depends on the graph structure of which is induced by lambda and its edges. Okay, so I mean, basically, what you have is that okay, like if you take this transformation between these two state space, it's bijective, and it conserves the Hamiltonian. So therefore, well, this implies that the partition functions are equal and that the log partition functions are equal. And also number of edges are equal, so there is not so much issue, okay, why this is true. Okay, so now what we have because of this is that f of dn plus 1, it's okay, larger because of superadditivity. It is larger than the sum over I in 0, 1 to the d of f dn I, and this is equal to 2 to the power d f of dn. Okay, so now this means that 2 to the minus dn plus 1 f of dn plus 1, it is larger than 2 to the minus dn f of dn. And therefore, what we have is that the limit when n go to infinity of f bar of dn over dn exists. Okay, it's an increasing sequence. Okay, this is just the volume of my cube. Well, the inverse of the volume of my cube. Okay. I have a d-dimensional cube. It has diameter 2 to the power n, so its volume is 2 to the power dn, the number of vertices. So, okay, basically, superadditivity, which I'm using superadditivity for disjoint union of 2 to the power d sets instead of 2 sets. But you know, this is something you can prove by induction, that superadditivity will be valid for disjoint union of k sets for any k. Okay, just prove it by induction of k. On k. Okay, so okay, now we have proved that the limit exists again some subsequence. So what we are going to do now is to prove that well, if lambda converges in the Van Hove sense, then yeah, f bar of lambda over lambda converges to this thing. So far, so good? Can I erase here? Okay, so this is lambda. This is lambda n, okay? Now what I'm going to do is, okay, what I'm going to do is to take k large, okay? And the idea is that k is large, but n is much larger than k. Okay, so n will go to infinity before k is going to infinity. So what we are doing is now fixing a k, okay, and dividing lambda n into big cubes of diameters 2 to the k. So what should we do? What we do is we define dk z, which is equal to dk plus 2 to the k z. Z belongs to zd. Okay, and I will just split my lambda into cubes like this. And try to cover it completely. Okay, and the idea is that there will be cubes that are completely inside lambda, and okay, I'm drawing lambda connected. It's not in the definition. Okay, it's just easier for the drawing. Okay, so lambda is not connected. It's not simply connected. It doesn't have to be connected. It's just that yeah, I'm making the drawing as I can, and you will see that I will not use any assumptions that are not simply this Birkhoff convergence. Okay, so these things are the d and z. Okay, I'm varying z here. So what I have is that really with this definition, zd, it's the disjoint union over z in zd of dk z. So okay, what I'm going to do now is basically to prove something about the lim sup, and then prove something about the lim inf. Okay, so just bear with me. Now we are doing something about the lim sup. So we'll just worry about one inequality in one direction, and then we will do something about the other direction in a very similar manner. Okay, so therefore what we have is that lambda, it's the disjoint union over z in zd of dk z intersected with lambda. Okay, and we can rewrite this disjoint union in the following manner. So it's the union over the Z in ZD such that dkz is included in lambda of dkz intersected with lambda, but which is equal to dkz. And then, okay, so these are the red cubes. Okay, and then I say that this is this union, well, the rest. So the union over, well, Z in ZD such that dkz intersected with lambda c is different, and dkz intersected with lambda. Okay, so this set here, I'm going to call it gamma. Okay? Okay, so basically gamma, it's just, you know, this. And the idea is that gamma doesn't count because its size will be small with respect to the whole box. Okay, so what we have is that f of lambda, okay, let me call it lambda n, okay? Lambda n, lambda n, lambda n, lambda n, lambda n, and gamma n. So f of lambda n, okay, it's larger than the sum over Z in ZD such that dkz is included in lambda n of f dkz plus well, plus f of lambda. Okay, so now what I have is that, okay, so let me write it. I have log of z lambda n, okay, okay, plus beta e lambda n. Okay, this is just my right term here. Well, this is equal to and then, okay, what's the number of cubes here? Maybe I should not worry too much about it. So first, this is larger, okay, than the sum over x in gamma n of f bar. Okay, so this, to get a lower bound on this thing, I can just atomize it. Okay, so what I'm saying is that, well, lambda n is just a union over all the singletons. which of elements that compose it. And the f bar of a singleton is just f bar of the origin, okay? F bar of D0, if you want. Okay, so here I get gamma n times f bar of 0. Okay, this is my second term. Now, well, what's the volume of lambda minus gamma? Well, it's the volume of lambda minus the volume of gamma. Okay, so the number of cubes, it's basically the total volume divided by the volume of a cube. Okay, so this thing here is just the number of z such that dkz is included in gamma. Okay? Because this is the total volume of the union of these cubes, and to get the number of cubes, you just and then you get f bar of dk. And then you get plus. Okay, so I think we are getting close. I should write my equation here. So now I get that 1 over lambda n log of the lambda n. It is larger than, okay, what I get is f dk over dk. This is the first term. And then I get plus lambda n over lambda n f of 0. And then I get minus f of dk over dk. And then I get minus beta e lambda n over lambda n. Okay? Okay, so now what I want to do is basically I want to lower bound. So I'm going to take the limit here. Okay, and basically I know that all my things with respect, when n goes to infinity, all of these things emit limits. So, well, this is a constant in n. This goes to 0. So why does this go to 0? Well, it's simple. It's because if you look at lambda n, okay, well, it's smaller than 2 to the dk times the size of the boundary of n. Why? Well, it's just that it's 2 to the dk times the number of green cubes. Okay, and for each green cube, you have at least one vertex in the boundary. Okay, so remember, we are fixing k and letting n go to infinity. So this thing, okay, depends on k and on n, but when k is fixed, this means that this is up to a constant, just the thing that goes to 0 in the definition of the Van Hoff convergence. Okay, so what we have is that lim inf, sorry, when n go to infinity of 1 over lambda n log z lambda n, it is larger than f bar of dk over dk plus 0 minus beta d. Okay, and now we can say that this is larger than the limit. Well, we can make k tend to infinity because this is valid for every k. So what you get is that, okay, where should I write? Lim inf of f log z lambda over lambda. Okay, where lambda goes to zd is larger than the limit when k go to infinity of f bar dk over dk minus beta d. Okay, so now we just need the other bound to conclude. Okay, so that's, I know, okay. I will just leave you enough time to rewrite things, don't worry. But what I'm going to do is just use the same equation, but now with f hat, which I know is submultiplicative. Okay? And this guy here, I will bound it by from above by gamma n times f hat of 0. Okay. So let's see now if we can do things cleanly. Well, everybody agrees with that? Remember that f hat of lambda, it's just the log of z lambda. And this time I'm taking minus e, minus the number of the beta times the number of edges. Okay, so this makes all the edge contributions, if you want, negative, because you have sigma x, sigma y minus 1 now. And this is sufficient to make everything subadditive. Okay, so now I'm going to write it like this. So okay, I will underline this is my modification. And now I get this, and I get this. Okay, good. Okay, so now I have the following. So for the same reason as here, okay, so I will just rewrite this. So I have 1 over lambda n log z lambda n. It is larger than f dk over dk plus lambda n over lambda n f0 minus f dk over f dk. And now I guess I have plus beta e lambda n over lambda n. And if I take n to infinity, what I get is that the lim sup over n going to infinity of log z lambda n over lambda n. The lim inf, no, the lim, yes, okay. The lim sup, it is smaller than f hat of dk over dk plus beta d. Okay, and this thing, it's the same thing as beta dk over dk plus e dk over dk times 2 beta, no, minus plus beta d. Okay, and now if you take k that goes to infinity, this goes to d. Okay, so you have beta d minus 2 beta d, so you get exactly this. So we get that lim sup when lambda increases to zd in the Van Hoff sense of log z lambda over lambda is smaller than the limit when k is go to infinity of f dk over dk minus beta d. Okay, so you see that with sets, things are a bit more delicate than with Fekete lemma, and in fact, we need to use both superadditivity and subadditivity. Or you can use basically superadditivity and something else that basically tells you that when you're using subadditivities, you're not losing too much. Okay, so the proof in the lecture notes, I mean, in spirit, it's the same. In the details, okay, I've written it a bit differently. But, okay, partially to make it possible to write it on the board. Okay, so it has a bit less computation than the one in the notes. But, okay. Okay, so now we are going to explore a few corollaries of this theorem. So any question on the proof? I guess we're all good. Okay, so this was the hard part for today. Okay, so what we have is that okay, so it's more an observation than a corollary. So I mean, we've obtained f beta h as a limit of convex functions, so it's convex. And also, it's symmetric in H. And the reason for this, okay, it's simply because if you take the free boundary condition, then you have symmetry in H. Okay, so because here you can take any boundary condition, then in the end you obtain something which is symmetric. Okay, so now we are going to look at a second corollary. And okay, so for this I introduce okay. For beta positive, I introduce beta, B of beta, which is the set of H at which so it's the set of H at which f beta H is not differentiable. Okay, so I fix beta, I look at this as a function of H. An observation here is that this thing is at most countable. This set is at most countable. And okay, this is a standard fact of convex analysis. I mean, the idea is that you know the derivative of f is increasing. The set where the derivative is not defined, it corresponds to the jumps of the derivative. Okay, and you can have at most countably many jumps, because if not, then the sum of jumps, basically, the sum of the amplitude of the jumps would be too big. Okay? The idea is that in a given interval, the sum of the jumps, I mean, sum of amplitude of the jumps has to be finite, okay? And if in some interval it's not countable, then the sum would be infinite. So therefore, you would have a contradiction. Okay, so for those who are not really comfortable with that, this is detailed in the appendix B of the lecture notes. What we want to say is that basically, outside of this set, nice things happen. So what do we mean by that? Corollary 2. For H not in B beta, we have that the limit when lambda converges to ZD in the Van Hoff sense of the empirical average of the magnetization it's equal to m beta h, where m beta h is simply the derivative with respect to h of beta h. Okay, so I mean, remember, we are interested in taking the large volume limit of the system. Okay, so ideally, the best thing we would like to do is to be able to look at really the limit of the measure and to define it as a measure on the set of spin configuration on ZD. But before doing it, maybe we can be more modest and look at the limit of like some relevant quantities of the spin configuration in the box, like this empirical magnetization. Okay? And basically, this corollary tells you that, well, you can prove that this average magnetization, it converges for all but possibly countably many values of H. Okay, so what's the proof of this? Well, we already know that if you take the derivative with respect to h of f lambda beta h, then you get eta here. Then you get the average of the empirical magnetization. Okay, it's something we have seen last time. So basically, the result is something about taking this to the limit. Okay, so basically, I'm asking to interchange limit and derivatives, and this is usually the thing that you're not invited not to do. But it's the case that for convex functions, you can actually do it. So let me write and prove the corresponding statement, and this will just be the proof of the corollary. So okay, so this is possibly the missing piece. Okay, it's here. Okay, so if okay, so let's consider a function on R. I could restrict myself to an interval. I would have the same result. So it's not the most general thing possible, but I think if you understand this proof, basically you know how to generalize it a little bit to other situations. If convex and okay. Let's assume that phi n is C2. It's also not completely necessary, but so let's, here in our case, this thing is C infinity, so we don't have problem with this. So what the result says is that if the derivative of phi exists, so if the limit is differentiable, then phi prime of n converges at h, and the limit when n goes to infinity of phi prime of n of h is equal to phi prime of h. And this doesn't work the other way around. Like, if this converges, then this might be false, actually. Okay, if this converges, it doesn't imply that the derivative exists. Remark, phi prime n of h can converge without having phi differentiable at h. Okay, so okay, and if you have this lemma, then you're done, because basically, if you take the limit here, okay, if you know that f beta h is differentiable, then f beta h is exactly the limit of this along a sequence that converges in the Van Hove sense. And then this implies that this, okay, has to converge to this, to the derivative. Okay, so. What we have is that lemma implies a corollary. Okay. So now let us prove the lemma. And okay, so we are going to use convexity. So what we are going to do is basically to prove something separately about the lim sup and the lim inf of phi prime n. So what we have is that by convexity, phi prime n, well, it's smaller than the slope of a chord which is to the right of h. So it's smaller than phi n h plus u minus phi n h over u for any u positive. Okay, so now this means that the lim sup of phi prime n of h when n goes to infinity, well, this is smaller than, okay, this converges. I know that phi n converges to phi at every point. So this limit is well defined. This is just phi of h plus u minus phi of u over u. And I make u tend to 0, and I get that this is equal to, okay, so then I make u tend to 0 plus, and I get that phi prime n of h, it is smaller than the limit when the lim sup when n goes to infinity of phi prime n of h is smaller than phi prime of h. Okay? Because phi is differentiable, when u goes to 0, this goes to phi prime of h. Okay, the lim inf is exactly the same thing. So what I have is that phi prime n of h, it is larger than, well, the slope of the chord to the left. So phi n h minus phi n h minus u over u, u positive. So what I have is that the lim inf of phi prime n of h when n goes to infinity is larger than phi of h minus phi of h minus u over u. And then I make u goes to 0, and this converges also to phi prime of h, and we are done. But I mean, in fact, if you don't remember this, so if you don't remember the proof of it, sometime you can just try to find it by yourself. It's a good exercise of calculus, I guess. Okay, so in fact here we have proved slightly more than what the lemma says. what we have proved is that the lim, okay, let me write lim sup like this, so that's the lim sup. Okay, and I will not write the ends, so of f prime n of h. This is smaller than phi prime h plus. This is smaller than the limit inf of phi prime n h, and this is larger than phi prime h minus. What are phi prime h plus and phi prime h minus? It's just the limit of phi prime when h goes to h plus. When a's goes, when the limit of phi prime of h when a's go to, well, okay, when the limit of phi prime of u when u goes to h, but taking superior values. Okay, and this is the limit on the right, okay, and this is the limit on the left. And this limit exists, okay, just because on its set of definition, which is the complement of something countable, so in particular it's dense, on this on the set on which is defined, phi prime is increasing, so you don't have a problem to define the limits. Okay, so this is true without the assumption of convergence, and of course, when phi prime of h is defined, these two things are equal, so therefore you have a limit there. And maybe as an exercise, okay, so yeah, an exercise you might check that it's possible that all of these inequalities, they might be strict. Okay, so I mean, you might think, okay, maybe if I have this is because the lim sup is equal to this, and the lim inf is equal to this. In general, this is false. Okay, you can have the lim sup to be, and the lim inf to be equal, and them to be equal to this, or both of them to be equal to that, or you can have strict inequalities everywhere. Okay, so you can just see that this is the best you can get in general. Okay, and in the case where phi prime is differentiable, we have this convergence. Okay, and yes. Which remark? Okay, so yes, but this is kind of part of the exercise if you want. So you can try to play with. Okay, so let's take first define phi, and then you try to define phi n. So phi is equal to. Okay, okay, maybe x plus. Just this function. Okay, and then you can just wiggle it a little bit. So phi n is equal to x minus 1 of n plus. So I guess at 0, phi n is always differentiable, and the derivative is equal to 0. Okay, but here in the limit, you get something which is not differentiable. I think basically this example solves everything. So you can also use it in the exercise and it will work. Okay. Yeah, what was the last thing I had to say? Yes, so now let me move back to this notion of phase transition. So how did I write this? Yes, so okay, so basically a corollary of the corollary, or a remark associated to the corollary, is that if H belongs to this set of nasty points, for all we know, this set might be empty, but okay. It turns out that it's not, and that's the reason why. Okay, it turns out that with some assumption it's not, and this is what makes the model interesting. But okay, on this set we can say something. It's actually that if at some point m beta h is not defined, actually it's always defined to the right of this point and to the left of this point. And well, if you take the limit to the right of this point, what you get is really the derivative on the right. And if you take the limit to the left, it's equal to the derivative on the left. Okay? So the magnetization, well, it's not defined everywhere, but it's defined on a dense set, and it's increasing in H. So on points where it's not defined, basically, you can define the limit on the left, the limit on the right, and the limit on the left. Okay, and the idea is that if you're not differentiable, then this is strictly superior to this. So what's happening is that when you vary H continuously, okay, when you go through a point of this set, the magnetization jumps. Okay, so on a finite box, magnetization is of course a continuous function of H, but here in the limit, it's possible that we observe discontinuity. To prove that we observe discontinuity at some point, we need to show that this set is non-empty. Okay, and for some reason, we will be really interested in the case where the case of H equal to 0. So for that reason, we will define m star of beta, which is the limit when H goes to 0 plus of m beta H, okay, which is something which is larger or equal to 0 just because my function is symmetric. Okay, and this is what is called the spontaneous magnetization. Okay, so m star of beta, it's equal to 0 if and only if H does not belong to B of beta. if the function is differentiable at 0, then the derivative has to be 0 because it's symmetric. And now the idea is that this spontaneous magnetization, it really corresponds to what we had in mind in this experience of Curie. It's basically a magnetization that remains in the magnet even though you have no external magnetic field. Okay, so we'll see later exactly okay, to what it, I mean, how to obtain this as a function really of the measure of the Ising model. Okay, as a function of this measure on spin of spin configurations, but yeah, I mean basically what we would like to show is that when at high temperature, so when beta is small, this is equal to 0, and when at low temperature, so when beta is large, this is positive. Okay, and if we do that, basically we have kind of it means that the model is good in the sense that it kind of gives an explanation for this this physical phenomenon of spontaneous of magnets that keep their magnetization even though they are not in submitted to a magnetic field anymore. Okay, so okay, let me tell you what we are going to do next time. So what we have said so far is that m lambda, if you take its average, okay, then this behaves like m beta h, okay, when lambda goes to ZD. Okay, if h does not belong to beta. But if you've ever had the magnet in your hand, okay, you know that its magnetization, it's not something which is random. Okay, so basically, on a large scale, what you should have is not that m lambda is, its average is, okay, behaves like some value in the large volume limit. It's really that also if you look at it, okay, as a random variable, it should be actually very concentrated around this value. Okay, and now the question is, okay, can we prove this? And it turned out that the partition function is exactly the right tool to do this. So not only we have this, but m lambda is actually very strongly concentrated around its average. Okay, so what we are going to show so theorem is that if H does not belong, so if my free energy is differentiable at H, then what I have is that, okay, and lambda n converge to ZD in the Van Hoff sense, then what I have is that this thing, okay, so for all delta positive, there exists n0 of delta. I guess, well, okay, I guess this n0 also depends on the sequence of boxes you're using, but this is kind of implicit. It probably also depends on beta and h, but I mean, these also are fixed parameter. And what I'm saying is that these decays, and there exists C delta positive, such that this decay, like exponential minus C delta times the volume of the box. Okay, so the probability that you deviate a little bit from this magnetization, it's actually exponentially small in the volume of your box. Okay, so actually, for this result, you don't really need this, okay? But if you don't have this, you get a weaker result. So basically, the idea is that the probability of being larger than this decays exponentially. The probability of being smaller than this decays exponentially. But if these two things are not equal, you cannot say anything about the probability of being in the middle. Okay, so I think this is a cleaner result. So. And basically, why is it that you can prove this? Well, the important part here is that if you look at this, okay, so if you look at the partition function for a value that is a bit larger than h, okay, what you actually get is the Laplace transform of the magnetization. Okay, where here m lambda is equal to, well, just the same thing as a small m, but I'm just not normalizing. Okay, and basically knowing something about the Laplace transform of a random variable, this is really what allows to know about, well, the probability of being larger than its average. Okay, so this is what we are going to do next time. So, okay, so we'll start from this. You can try to prove it by hand. I will also prove it tomorrow. And using this, we will see how you can get, well, exponential bounds on probability from deviating, for probability to deviate from the mean. Okay. Any questions? Ricardo? No? Okay, so I guess we can stop here.